So, to really get a sense for these objects, nothing is better than an actual tour. Luckily, a virtual tour to a black hole. Our tour guide is Andy Hamilton of Colorado University, who has generously let us use these beautiful simulations he's made. So we are going to approach this little system of stars. We've got a 60 solar mass blue main sequence star with some other smaller, younger stars, and orbiting in a binary system with this blue star is a 30 solar mass black hole, which of course we can't see. And 30 solar masses tells us its Schwarzschild radius is 30 times the sun mass, 3 kilometers. And this is an image of our trajectory. We are going to be in free fall, so we're going to be accelerated towards the system and fall into an unstable orbit at 2 Schwarzschild radii. That is a zero energy orbit, so you can actually freely fall without any engine power into that unstable orbit. You don't want to miss, because if you miss by a little bit, you either get flown back off to infinity or fall into the black hole. Of course, since it's virtual, we'll manage to survive it either way. But let's start by approaching the system from a distance and seeing what the effects are of coming close to a black hole. So I start the simulation, and we are falling from 100 million kilometers. As we approach at about 100 Schwarzschild radii, the lensing of the black hole produces what is called an Einstein ring, a donut-shaped image of the blue star, which is formed by light lensing and bending all around the black hole. And as we get nearer, we see multiple lensed images of all of the stars, because remember, we are now at, this clip ends at 3 Schwarzschild radii, the last stable orbit. Deflection of light is significant, and we see these multiple lensing effects. Notice that on the bottom, on the horizon itself, the animator has superposed this nice red grid for us. Of course, the actual horizon does not have a red grid on it, and if it did, you wouldn't be able to see it. But this just tells you where the Schwarzschild horizon is. And the interesting property is that because of the deflection of light, note that you can see both poles of the horizon. So you can see all the way around it because light is so greatly deflected. And so that was us at the last stable orbit at 3 Schwarzschild radii, but that is for sissies. We are heading down to a 2 Schwarzschild radius orbit. We are now orbiting the black hole at 2 Schwarzschild radii. We see all of the enhanced lensing effects that I was talking about. We see multiple images of all of the stars in the cluster forming and disappearing. If you want to know, the proper time period of our orbit is about 4 milliseconds. To someone viewing us from far away, it's a factor of 2. Note, we're at 2 Schwarzschild radii. The gravitational redshift factor is a square root of 2, but there's another square root of 2 because we are moving at about 0.7 times the speed of light to maintain this orbit at 2 Schwarzschild radii. You can compute both of those things. So looking from afar, we would appear to be orbiting at every 8 milliseconds, where in fact we think we're orbiting every 4 milliseconds. The tidal forces at this point are, I believe, 100 times g. So your feet are pulling on your head with 100 times their weight. You're getting a little bit uncomfortable, I should think. And then these white dots are a probe that is being dropped conveniently 400 kilometers ahead of us down onto the surface of the black hole from rest. And as we approach it, we see it falling down because it's dropped ahead of us in orbit. And we see it falling down. And what we see is, this probe is a sphere, and we see the tidal force stretching it out till it's no longer anything like a sphere. And second of all, we see that as it approaches the Schwarzschild horizon, it is reddened and slows down. The bit that is closest to the horizon appears to stop falling first, and eventually it turns red and merges with the horizon. We can't see it because the redshift is infinite, even between the Schwarzschild horizon and the orbit at 2 Schwarzschild radii, where we are. And now, well, this is unstable, but not dangerous enough for us. We're not here for the tourist version. We're going all the way. We're going to fire the boosters, slow ourselves down slightly, and land on, well, not land, but penetrate through the surface of the black hole. We just crossed the horizon, and at the point that we cross the horizon, within about 1/10 of a millisecond, we are going to be hitting the singularity for a 30 solar mass black hole. The g-forces at the Schwarzschild radius for this 30 solar mass black hole are 1,000,000 G, so we have long since been decomposed, and as we fall through the horizon, we will meet anybody who fell through just before us, and we have a tenth of a millisecond to have a deep conversation with them before we hit the singularity and everything ends. So this was a quick tour of a black hole, and you live to tell.